the net pushes up on the person. Okay, so the result was the net moved downward, right? Okay, what's the result of the person? What was the, huh? He could, depending on the relative forces of the net, and that would have to do with the elasticity of that net. He would either boing, okay, or he would just stop his motion. The critical thing there is his motion will change. Actually, I think it's girls that were trapezes, isn't it? So her motion will change as she hits it. Got it? All right, let's look at the airplane. I'm going to draw this one a little bit. Let's kind of think about the forces acting on this airplane. And it says that it's flying in a completely horizontal plane without falling or rising because it interacts with the air. Okay, so let's talk about all of the forces acting on this airplane. We're going to say it's moving this direction, to the right. Okay, what are the forces? Yes? We're going to have a lift here that's keeping it up in the air. Yes? Drag force. It's going to have a air resistance here.
Gravity.
The gravitational force, or the weight, will be acting down towards the center of the earth.
The applied force, or the force that's making it forward.
There's going to be a force due to the engines here, okay? So in this situation, we are going, and it could be called a force applied, it could be labeled anything. Okay, in this situation, we really aren't looking at these. I'll just kind of... tell me about the force. Okay, what should the first one be? The action. What does the air do to the airplane? Let's talk about the air. Pushes back on the airplane, okay? What about the airplane?
Pushes down on the earth.
But that's not the reaction to the air, is it?
No, we're talking about the air.
Okay, so if this is, all right, wait a second. Is this the airplane or the air? It's the air acting on the airplane. When you put a free body diagram, you're going to be writing what acts on it by something else. So that's the air acting on the airplane. We know that the airplane, if we have air, the airplane is going to be pushing forward on the air, you know, kind of like in a swimming pool, kind of paddling off. Okay, that's the action-reaction, is the air pushing back on the airplane pushing forward on the air. If it's moving at a constant acceleration, these two are equal. All right. Let's look at the gun and the bullet, the next page. This is sort of a momentum problem, but we can think about it either way. I like it best to look at gun and bullet here together, and then I want to look at the gun and the bullet. Okay, so up in that top picture, what's happening? What are the net forces on the gun and the bullet?
Applied force on the bullet by the gun.
Up in the top picture? You have nothing, okay. So then in the second picture, you have a force. Let's talk about the bullet. What's happening to the bullet?
It's for the outward motor. The gun.
Okay, so the bullet's going to have a force this way.
It pushes back on the gun too. So.
Yeah, anyone who shot a gun has felt it in their shoulder the next day, right? That recoil velocity, okay? Are those forces equal?
Is it no, because the bullet's going to accelerate?
That's not.
Okay, so you say no because the bullet's going to accelerate. But, and I agree that the bullet's going to have more acceleration, but at the instant that it leaves the gun, at this instant when they were just there together,
Yeah.
these are going to be equal and opposite. then they're going to behave differently because the gun has so much more mass, it will not accelerate as much as the bullet. But the force was the same. Separating that idea of acceleration from the force. All right, I'd like you to start on the next one, and let's draw that free body diagram. I want you all to draw it, and I'm going to come around and look a little bit. We have students A and B pulling on that rope. Okay, so one of the more important things here to learn about this system is that, well, there are a couple things we need to really take note of here. All right, you are going to be asked to do a free body diagram on the AP exam. Guarantee it, 100% chance. It's not a question. It's one of the requirements of the exam. Okay? Not a question. And I just graded a test of my students, and I said, how could y'all have missed the free body diagrams? That was 12 points of drawing arrows on boxes, okay? This should be something you master. The first rule, there are two rules on the picture that they've given you there. One, I have seen arguments go on for an hour over how close the arrows are to the dots. So your arrow must touch your dot. No question. This will not get you credit, okay? You have to have it go all the way and touch it. The other thing about this diagram is that when they give you that grid, your vector size must be proportional. If they don't give you a grid, your vector size does not have to be proportional, but if they give you a grid, your vector size must be. All right, so let's talk about student A and student B. All right, what force did I just draw?
Gravity.
I drew the weight. Okay. How would, is that a good way to label it? Force of the weight, gravitational force on A. How would you label it? W would be fine. If you go much farther afield than that on the AP exam, because there are people from all over the place grading them, you need to put a little key over here, and you can just say W equals weight. And it can be very simple, but you need to make sure you don't ever lose a point because you label things slightly differently from how that teacher who's grading it does, okay? It's an easy thing to do. It doesn't take but 2 seconds. Next thing. All right, so what are the other forces acting on A?
Normal.
Normal. How is its relative size going to be?
Equal to weight.
Equal to the weight. Yay. Okay, there it is. I tend to label it FN. You have a tension. Which direction is it going for student A?
Right.
To the right. Anything else?
Friction.
Okay, which direction is it going?
To the left.
Is it larger or smaller or equal to the tension?
Larger.
Why is it larger than the tension? Because it's accelerating. The net force on this person is going to be to the left with the friction because he won. How about B? We're going to have the weight again. Is it going to be the same as for A?
No.
Hmm?
It would be low.
It's going to be less, smaller person. We'll have the normal.
And there'd be less tension as well. Right, not tension, friction.
There'd be more tension than friction.
There'd be equal tension, it's a third ball there.
Equal tension, but.
Equal tension, but there's less friction.
Okay, so all who say tension's equal,
Yeah.
Tension would be
Everyone?
equal.
Yep.
okay, but you think friction
It's low.
is less
Because
than the
friction's based
tension?
on weight.
Actually, that's not the reason here though. Friction does depend on that normal force, but the reason that it's greater here is that the net acceleration is to the right or left. That other right. Okay, so yes, we're going to have an equal and opposite tension. It's exactly the same going the opposite direction, but we have a smaller force friction because we know that the acceleration of everything is to the left. I want to show you one quick method for looking at some of these systems, and then we're going to do some multiple choice problems, but the other students I've shown this to have found it very helpful as they look at the multiple choice. So y'all have 5 minutes of you in you just to listen to me? Maybe less than 5. How many of you cringe when you see this problem? And what do they always want to know? The acceleration of the blocks, let's just say it's frictionless, and they want to know the contact force between those blocks. How would you do it? Where would you start? Okay, so there are 2 ways of approaching this. Okay? We can do a free body diagram of each, okay? And so this one would have, I'm going to use 10 for G, which you can always use on the AP exam. So this is going to have 20 newtons of gravitational force, and it'll have a normal, oh, I forgot, it's being pushed by 10 newtons here. Okay. All right, it's got a 10 Newton force. Remember, you always push your, that's an applied force. You push your forces through. They always come out of your free body diagram. Okay. Then, what else is acting on that one?
You said it's frictionless, right?
Uh-huh.
There's a force from this free block.
Okay, so this is the contact force. All right. On the 3 block, we're going to have 30 newtons of force and a normal. Okay, what else is acting on this one?
Contact force.
In which direction is the contact force going to go? To the right. And it's equal and opposite. So one way of doing this is going to be to say this net force equals mass times acceleration for each one, right? And so that's going to be 10 minus the contact force is equal to 2A, have 2 unknowns. This is going to be the force contact equals 3A. Are we all good with that? All right, so now we're going to have to substitute in this force contact right here, which is not all that difficult. 10 minus 3A equals 2A. 10 equals 5A, and A is 2 meters per second squared. Or you can look at the inertia of the system and the net force. And the way I think about this is I draw a box around my system, and that's going to be my new free body diagram. So this has 5 kilograms of inertia, correct? And it's being pushed with 10 newtons. Those contact forces are internal, right? F net on the system equals MA, 10 equals 5A, A is 2 meters per second squared. If you can understand that, it's just a little bit more efficient, and it's a nice way of looking at the inertia. It had more inertia than just the single block. Because sometimes you'd like to take that 2 kilogram block and just say F equals MA, and that doesn't work. Okay, so let's look at the multiple choice. I want you to do 1 through 4 on page 5, please. Work with the person in front or behind you. Turn around. Work in pairs. Okay, so you put the answers in here. Y'all talk to each other back a little bit. Okay. Where'd y'all answers sit?
For what?
Mm-hmm. Was that system at rest?
Yeah, but they're still pushing on each other's force.
How is it?
It's not just like you said, when you pushed her and she started moving, y'all were still pushing on each other with the same force.
So then how is C the right answer? But that one wasn't moving. Under what conditions would it be moving with the force small? Does it matter if it's accelerating or accelerating? It's always, those forces are always in but you nailed the second one, and every time to have you, somehow you have to jump in there. Let's push down before pushing back up. Okay, y'all, those springs are scary. You haven't seen springs yet. Pretend they're strings, okay? They don't matter a bit in this problem. And you can figure it out from there. Just consider it's spring, it's strings, and it's tension. So look at it that way. Okay, so the best way, I mean, there's an analysis way you would do it that way. The best way to take that is to be, and that 1 kilogram, that behind here,
Well, like, if this 1 kilogram is having to prove 4, but this 2 kilograms is only having to prove 2. Like, this one's stretched. How would you, yeah, it's not 2.
Alright, and now I need to talk to you about springs. Y'all, here's my spring analogy. If you're afraid of springs, think about a rubber band, okay? Rubber band. You stretch it just a tiny bit, it has a tiny bit of force. You stretch it more, it has more force, right? It gets stronger and stronger as you stretch it more. That's all you need to know about springs for today. Yeah, because it gets more force. That's what I was trying to How are those doing? They're not doing. Why aren't they doing? Oh. Why those rebels? More or less. Maybe we'll focus on this.
It's always been a race for
Try to be careful about Well, if I think about it, let's think about the inertia of this. Okay, so 1 kilogram is less than nearly all inertia. So that is inertia. 4 kilograms is back. So they're getting more stretch. All right, so this one, you're going to say, do it my system way. Okay, so 20 equals 5a, right?
Right.
So the acceleration is 4. And then do kinematics. V is VO plus AT. And you have 4 times 2, which is 8. Does that make sense? So that system works really well with something fast like that.
That's what you remind me of.
Oh, there is a VO plus AT is 1 unit. Or VI plus AT.
All right.
She's a class woman.
Y'all got ready to move to the incline plane?
I got eight.
It is not. So you have 20 and 5 compressed air. So 20 times 5 Is that what you thought? Oh, y'all arguing?
He just wasn't telling me what he was saying.
Okay.
Just show me that, buddy.
Y'all ready to move on to the incline plane? Move along.
No. I work in the college, but since
We got
pulling
inertia.
this one too, it's four acceleration. So the force is 20, the mass is 4, and then you got, I got 4 and then it's force over mass, or mass over force.
So that one,
Wait, so we have 50 newtons in our shirt.
Alright.
does that make sense?
Yeah, I had to eat and then she
How we doing with the incline plane? Do we need help? Huh? You got it? What'd you get for the incline plane? And why it's 2? Actually, what's happening here is you're still cooling down. This has the same cooling force. That way. This would have 2, would have and three kilograms of inertia. So 6 is 3A.
20 newtons is force. We got 5 force. 1 over 5 is 4 meters per second. And the question said you're going 50 seconds. So you get 8 meters per second.
Those of you who need it know what to put on the front. Okay, let's look at that incline plane. How are we doing? Have you looked at the incline plane? Get it? Y'all, because of the incline plane, I'm going to explain it to all of you for a second. was accelerating down the incline at 6 meters per second squared, right? What causes that acceleration?
Gravity.
Well, a piece of the gravitational force. Which piece of the gravitational force? Huh? Yeah, the part that's parallel. So if the gravitational force comes here, then this piece right here is going to pull it down. And it is proportional. I mean, this is mg, Fg equals mg. And this is actually mg sine of theta, but we don't know theta, so we can't really do any math, right? But you can recognize that this force equals 1 times 6, right? So how much is this force? 6 newtons. It has to be. The net force is 6 newtons. Okay, so now if I have a 2 kilogram, all right, then what is the acceleration going to be?
It shouldn't be.
It's still going to be 6, because if we look at this from a variable point of view, we can say the net force equals ma, right? Now we knew that the mass was 1, but I'm going to keep it just as m. So I have mg sine of theta equals ma, and I divide both sides by the mass, and I find that the mass does not affect the acceleration when it's frictionless like this, okay? So it's going to, this situation on the same incline with a different mass will have an identical acceleration. Right? Okay, how are you going to do that part where we decided to put another block up here? F equals ma. Okay, so what change did the force acting to accelerate this system change? No. Okay, so my force is 6, right? My force is 6. What's my inertia of the system? 3. Why? 2 plus 1, yay. What's the acceleration? 2. Does that make sense?
Really, so 6 is 6 meters per second squared. That's our acceleration.
Right, it was our acceleration, but it was also our force because it was multiplied times 1 kilogram. This was 1 kilogram mass.
Yeah.
So 6 newtons and 6 meters per second squared. All right, y'all take a look at that next spring problem. At least get the 3-body diagrams drawn. Y'all gonna do this one? Important. You were just practicing.
Still working on that.
Good shirt. Fun fact tonight. Son is president of from Manhattan.
Is that the top?
They're talking about 1 and 2. And they're actually asking me.
That's so cute.
Excellent. Are they very far?
Okay, that's what I had first. Yeah, one's going down. Sam, she said that's right? Okay.
That's what I did.
Well,
Well, I did too, so they're probably wrong, but it's fine.
that's right, you need that spot.
Okay, so it's the same, like, what happens between, like, it gets us here, it's stretched out, like this.
Actually, yeah,
That's what I did.
exactly. So, that, okay, so the correct answer,
With these?
perfect. No. Let me draw. Okay, so 1 is at the top and 2 is at the bottom. So they each have, they're identical, so they have identical weights on them, right? Okay, and we're gonna have a spring force that's gonna be equal and opposite. And 1 is the top one, so that's going to be pulling it down. And 2 is gonna be here, and that's gonna be pulling it up.
Should it be greater than the force of gravity?
Yeah, it should be.
Since 2 moves up. So getting pulled up. Sorry.
Good job, good catch. All right, is the system in free fall?
Nope.
Is the whole system in free fall? If I did, okay, so let's just pretend that I have the 2 blocks and I like make that my system. What's the net force acting on that?
The whole system is.
The whole system is free fall, exactly. Because the only thing acting on this are the gravitational force of block 1 and block 2, right? That spring force is internal to the system. So if you look at the whole system together, it's in free fall. The center of mass of that system will be going down. All right, I want us to get to the lab question, and I'll tell you why. I have been assigned as a reader to grade the lab question several times. Actually, I design the rubrics and I write them, and I thought maybe I could help you with it and help you know what you need to do to nail this question. Guarantee if you're in AP Physics 1, you will have a lab question, and they're hard, and this one is kind of hard. So I want you to read over it. I want everyone to jot down with your friend one idea for an experiment. They're asking you to find an experiment that will demonstrate Newton's third law. I'm on page 7. They will demonstrate Newton's third law. So look, y'all get a little consensus among you, and then we'll try to come up with what our experiment is going to be and how you would complete this.
We just chest bump. If we went on chest bump, we came backwards, it would show that we went in, came back, and just chest bump. That's the only thing you have to do.
My math.
That's gonna be extremely scientific. Extremely scientific. I'm sure that's gonna get you a lot of points.
Yeah, if you have 2 blocks and you just throw them together.
Yo, we have materials. No, we don't. Yeah, we do.
Oh, we need to stop for it.
Alright, we're gonna use,
Oh, what if you teach you? Oh, let's use the cards. Let's teach you some cards.
let's use the stopwatch.
I know.
We need to be interested.
How big are these cards?
Little crotch rock.
Alright, so
Slam each other.
Yo, we don't need to be pushed. We can just add this. Okay, I showed you crotch rocks. You said
Right? We just get in cars and slam hard.
so, like an absolute value.
It makes it fun.
Another card.
That's gonna be, what's your experience?
No, but they have like different styles. And more like
Hello. Hey. Yeah, I got it right from
Yeah, we threw it out.
we added crotch rock.
We have a boy at the bottom of the ocean. Cards and just slam it. You shouldn't have
You know what we should do? Yes. Matt and that other kid. Garrett. They just run and jump into each other and then. I'm missing everything. Missing that. I'll stay away from you.
I like that. But how do we know where they?
You got your video camera with video and
Oh, like slow motion.
you got motion
No, we can use the elastic and the slingshot. No, we do have to have the balance. We gotta get the mass.
Okay, so let's get some of these ideas together. We will get back to equipment. I almost think you need to fill out that equipment last, after you've conceived of your experiment, okay? Otherwise, as they were in the back, let's add the video camera with analysis software. Well, hey, I love that. It is so much fun to do, but that might be a bell and whistle. It might not be critical to your experiment. You need to get the critical.
You never know what I'm doing.
That's right. Well, it might be critical to your experiment. I have several that it is critical to the experiment, but I don't know. We'll see if it is to yours here. The first thing I'm going to tell you is they're beginning to always say draw a sketch, but I'm going to tell you to always, 100% of the time that you get one of these laboratory questions, which you will get, draw a sketch of your setup. Y'all will get distracted in the middle of describing what you're going to do with the experiment, and you'll leave out big chunks of it. You just will kind of lose your train of thought, and you'll lose points because of that. The sketch solves that problem. It helps keep you focused, and that gives the reader something to look at clearly about how to grade it, and they can give you more points if they see that sketch. Oh, they did have that, they just didn't talk about it, okay? So let's talk about your experiment first, and let's draw the sketch, and then we'll go to the next step. What's our experiment?
Newton's third law.
Newton's third law, okay, yay! And I don't think the chest bump that I heard suggested is gonna work out well.
Oh, we got a new one.
I'm not sure I even wanna know.
So basically, we got 2 carts, each on top of like a hill.
You're putting them on a hill, you wanna draw it?
Wait, are we using hills?
How does this prove Newton's third law?
Let's go, Matthew.
Just draw what's on my paper.
That's the plan.
Make us proud.
Like this is the meter stick.
It's good.
Meter sticks always get bigger and smaller.
Yeah, yeah. There you go.
He's got me higher up, huh?
You want it to hit faster?
Right.
Oh.
So basically, you got 2 people in carts. They're gonna go
Video
down
camera.
at different velocities, and they're gonna hit somewhere, and then you're gonna see how far back each person is.
Perfect. That is a really good, this is actually a conservation momentum kind of experiment, which is really exactly the same theory as Newton's third law. So if you get asked for Newton's third law, conservation momentum also works. All right, so now we've got to, the very critical, this is what you always leave out. I think everyone understands the experiment, but what it says here is, outline, we want to, okay, mark, let's see. We need to label every measurement taken. It is the number one thing you will leave out. Okay, what do we need to measure in this experiment to get the data to prove Newton's third law or to verify Newton's third law?
Distance.
We need the distance. The distance that what?
They traveled and then how far back they
The final distance traveled by each, okay? I'm having more entertainment with them. Oh, did y'all see my name up there in case you needed it?
I'm glad you put it up there, because at first you were Marcia.
Yeah, that's what I wrote too.
It's fine. Okay, now you've left off half of the problem here, half of the question. What do we now need to put on?
How fast?
No. So we're still on this one?
Time.
No? What?
Card.
How do you measure
A
distance?
meter stick.
With a meter stick.
Yeah.
Okay, you've got to have how you measure it. Okay, you could have used a motion detector to do this too, but it's not necessary at all. The meter sticks works just fine and dandy. All right, then what else do we need to know?
Stopwatch. I mean, time.
What are you going to use time for? I think it's a good idea.
Well, it's like how fast they traveled.
Yeah.
Yeah, that's
Find their
fine.
velocity.
Oh, okay. Stopwatch
Yeah.
to find time. Do you want to find the time before the collision or after?
After. Right?
Before, so you can
Both. That is perfect. You said it.
All of it.
Either or.
Right? It's
Before.
It's before. I'm still with the chest.
Yeah.
One other way of doing it from before would be to use a meter stick to measure this
Yeah.
height. And that might be a little bit more efficient. And then you could use the v squared is vi squared plus 2ax. That would be another way of doing it. But this works fine. All right, we've got something else we need to measure here.
Masses.
Do mass.
Okay, how are we gonna measure masses?
You're gonna use a
Triple beam balance.
It's got 3 beams.
We'll measure the mass of the roller coaster park. Yeah, you should come to Denham sometime. We have full roller coasters and triple beam balance in the classroom. It's a spectacle.
Okay, so just to let you know how that's not even funny at my house. My daughter moved in with me a few years ago, and she teaches physics at another high school. Can you imagine what the conversations are like at dinner? Whoa! 2 physics teachers. So yeah, you should come to dinner at my house and hear physics. We good here? I think that should do it, okay?
Yeah, we got
So
it.
now the next section wants you to write a procedure. Again, if you're taking P2, you can't do it this way. But if you're taking P1, I will promise you you'll get more points if you'll go procedure 1, 2, 3, okay? Do it in a numbered list all the way down, okay? So what's the first thing you're gonna do in this experiment?
Measure distance.
Which distance?
The distance.
Okay, so let's go with collect all measurements, okay?
Okay.
Or collect, mass, what else do we need to collect?
Time. No distance.
We haven't started our experiment, how are we gonna collect time without an experiment? Someone else help him.
Height
Oh, you wanna measure the height?
of the starting height.
Okay, then what do we gotta do? We're gonna release some carts?
Yeah.
Ah, release carts.
As soon as you release, start your time.
Start timer.
I have a question.
Mhm.
If we do it in a list like that, like 1, 2, 3, do we need to write incomplete sentences there?
No, you do not have to, it's not required on
The
P1,
following
it is
students
required on
please
P2.
report to the level table. Nicholas Wagasback, Shamaria Hughes,
Thank
Megan
y'all.
Sunday,
I hope I've helped.
Caitlin
That's the
Trujillo,
only place on the
Bella
A3
Atkins,
that you need to write
Karen
complete
Collins,
sentences where they say in a concise
Nathan
paragraph.
That one has to be
Caitlin
complete.
Boutwell, and Rebecca.
Bullets can be used on P1
And we'll
or
put this
credit, so it
everything
does not
on
have to be
that
complete sentences on P1. Have I helped y'all with all?
Yes, ma'am.